Now, in this video, we're going to look at convergence of a power series, but only in the finite case. We're going to look at the endpoints of the interval, and we're going to look at the three different cases that can happen. Either there's no endpoints, or there's one endpoint, or there's two endpoints. Now, it's useful to develop a kind of intuition for this sort of thing, but it's worth keeping in mind that in a course-related setting, in a math course, you're going to have to prove your intuition, not just state it. So kind of keep that in mind. Having an idea of what's going to happen is not the same thing as proving that that's really the case. So let's look at our first example here. This is going to be our example where neither endpoint converges. And for all of these problems, we can use either the root or the ratio test. But since it is very common to use the ratio test, I will stick with that just for the sake of consistency. Now we have x minus 1 to the n plus 1 over 2 to the n. And for this case, oh wait, I have to do times the reciprocal, 2 to the n plus 1 times the reciprocal would be 2 to the n over x minus 1 to the n. And that's going to leave us with a limit as n goes to infinity. X minus 1 to the n plus 1 and x minus 1 to the n is going to leave me with an x minus 1, and my 2 to the n plus 1 and my 2 to the n are going to leave me with a 2. And for convergence, I need this to be less than 1. Now, all of these examples are going to have initially the same interval of convergence. The only difference is going to be whether the endpoints are included. So what we end up with is this x minus 1 over 2 absolute value to be less than 1. And so we start solving for our interval. Negative 1 to the x minus 1 over 2 less than 1. We multiply everything by 2. We get negative 2 is less than x minus 1 is less than 2. Our radius of convergence is 2. And then we add 1 to every side, and we get negative 1 and x and 3. Now, negative 1 to 3 is our interval of convergence, but what about the endpoints? Now, the thing about the endpoints is going to be determined by essentially where typically these are logs or polynomial components that are involved in the expression. If you have n factorial someplace, typically you're going to end up with one of the special cases, depending on whether it's in the numerator or the denominator. Same thing for the n to the n, things like that. If you've got other geometric components, those are just going to rescale your interval. Polynomial components or rational components or log components or things like that, those extra n's, they are not enough to alter the convergence inside the interval, but they do affect the endpoints potentially. And so in some respects, you can think about sort of where they are in the expression, but it'll be easiest to see what happens when we just look at the end. So we're going to check our original power series, but with these two endpoint values plugged in. So checking x equals negative 1. So we're going to plug -1 in here. And what that's going to give us is going to be, this will turn into a -2. And therefore, what we're going to end up with is n equals 1 to infinity of -1 to the n. Now, this is essentially going to leave us with the same kind of problem that we had in a previous video where we had n in the numerator. This is not going to converge at this endpoint, even though it's alternating. The alternating component is changing sign, and the sum is not going to go anywhere. If there's an n multiplying it, then it's going to continue alternating, but it's going to get bigger each time. And so you can call this the nth term test, because this limit is not going to 0, or you can apply the alternating series test, which says basically the same thing, that since the limit is not 0, the thing does not converge. So the limit of the terms are not 0. So by the test of divergence or the alternating series test, the limit or the sum does not converge, so it diverges. Now, if we do the same thing for the other endpoint, so we check x equals 3, then we run into a similar issue. If we plug in 3, then we end up with 3 minus 1 is 2, and therefore we end up with just 1 to the n. 1 to the n, of course, is 1. And so, again, we run into the same thing. The limit of the terms are not 0, and so it diverges. And therefore, we end up with the interval. Oops. Sorry about that. Hit the wrong button. Interval of convergence is -1 and 3. So that's one possibility, and that's not that uncommon. As I said, if you have any sort of n-type term, or none at all, and it's in the numerator, then it's going to do this. We saw the example in a previous video. We had an n in the numerator, and it did exactly this. It diverged at both endpoints. But even if there's no n, it's going to diverge at both endpoints, because that's what geometric series do. Now, we want to look at the case where only one endpoint is going to converge. So this would be an example of that. Now, again, this looks very much similar, except there is an n in the denominator here. Now, it's not an n that has a really large power. It's just an n. Now, if we do the ratio test, I can go back and I can swap a lot of this work. We're going to have in this denominator, we're going to have n plus 1. And then up here, we're going to have an n. And the thing is about these expressions is that what we're going to end up with is we're going to have a second component here for our n's that didn't cancel. We're going to have n over n plus 1. So we have an n here and we have an n plus 1 here. And the limit of n over n plus 1 is 1. So that portion is not going to determine sort of the overall convergence of the problem. Where this n will become important is where we check those endpoints. So we still end up with the same radius of convergence that we had before. I should say the same initial radius of convergence from the last case. But we have to check the endpoints. So let's look at those endpoints. So we got that our interval of convergence was -1 to 3. So now let's check x equals -1. So let's take our series and we're going to plug in -1. And that's going to give us -2 up top. And what that's going to reduce to is -1 to the n, because the -2, the -1 can be pulled out, and then the 2 and the 2 to the n can cancel, and I'm left with just this. This is the alternating harmonic series. And it converges by the alternating series test. Because the limit of each term does go to 0. Now, normally, again, if this wasn't alternating, this would not be enough. It has conditional convergence here. But because it is alternating, it does converge. And so -1 is a point of convergence and should be included in our interval. Now, if we do this with x equals 3, though, so we plug in 3, and then 3 minus 1 is +2, and then the 2's cancel, and we're left with 1 over n, because 1 to the n is 1. So we're going to be left with just the regular harmonic series, and we know from the p series that this does not converge. This is the harmonic series, and it diverges by the p series test. Now, of course, you could also do this by the integral test. But either way, you're going to get that this diverges. So the interval of convergence is -1 included, 3 not included. Now, if your original power series has an alternating component already, then you will have only one endpoint converge, but it will be the opposite endpoint. So if this was initially, let's go back to our original series. If this was initially -1 to the n times x minus 1 to the n and 2 to the n, or if this had been all of this, but it was -2 to the n instead of 2 to the n, then we would still have to do all these checks, and this limit interval of convergence would all be exactly the same, except that when I plugged in -1, I would get the harmonic series, and when I plugged in 3, I would get the alternating harmonic series. And so the endpoints would converge one of them and not the other one, but it would be the reverse. And then if we look at the last case, let's go back and grab that. Now, again, a lot of this is going to remain the same as in previous calculations. So I'm going to snag some of my old work to save on typing. But we're still basically running the same test. So this would be n plus 1 cubed, and this would be n cubed, and this would be n cubed. And you could multiply this out if you wanted, but it won't really change the fact that the leading term is still n cubed. And the limit of n cubed over n cubed, all the other terms are not going to matter, is still 1. And we're still going to end up with this. And we're still, because all the other pieces are still the same, we're still going to end up initially with that -3 to 3 interval. But of course, we have to check each endpoint. And when we do that, -1 to 1, and then this will be -2, and then the 2's are going to cancel. And we're just going to be left with -1 over n cubed. And so, of course, this converges by the alternating series test. And so the -1 endpoint has to be included. We saw that before. But when x is equal to 3, this will become 2 to the n, and 2 to the n just becomes, cancels with the 2 to the n in the bottom, and this just becomes 1 to the n, obviously, which is 1. And the denominator is just n cubed. But this end also now converges by the p-series test. So before, when we had only one n, it diverged because the p-series test. But here, the p-series test says it converges because the power of n is bigger than 1. So the interval of convergence is -1 and 3 with both n's included. Now, essentially, the framework here is that if you have an n, you're basically looking for a p-series. So if it is an n that is bigger than 1, it can be 3/2, it can be 1.1, it doesn't really matter. Anything bigger than 1, both n's are going to converge if that n is in the denominator. If it's only between 0 and 1, then one end will converge and not the other one. So there's some n 0.0001, that's fine. All the way up to n equals 1, then it has conditional convergence. One end will converge, but not the other. Or there's no n, or your n is in the numerator, then you're going to get divergence at both endpoints. And again, there are similar principles in case you have something else that is not a polynomial, maybe a log or something like that. The powers often end up working quite similarly, although you would, of course, have to actually conduct the test to verify that this is in fact the case, because it's not enough to kind of just intuit that there's a pattern, but you have to prove it in a math class. So, but that is the kind of thing that you're looking for, is if you have just this combination of the geometric series and other terms that don't behave, that don't converge as quickly, then you're dealing with, or don't blow up as quickly, then you're dealing with just those endpoint behaviors. And that's when you're going to have to work a little bit harder. Now, obviously, it's possible that there's other circumstances other than these where you will get this kind of behavior. So if you get a finite interval, you always, always, always have to test it. But when you have these very common scenarios, this is the kind of behavior that you would expect.